So, is it all right to start?
Hello, Professor. Okay, we
Yep.
got back.
Okay. Okay, thank you very much to get back here, and let's restart the second half of my lecture. Up to now, I was talking about the kind of nanoscopic world inside the lovely materials and going down to the polymer chains. And now you understand how polymer chain moves very rapidly, very quickly, very actively. Okay, and it's really like a liquid, although it looks like solid. But the case, at least the case of a lovely state, the polymer behaves like a liquid. Then, from now on, we turn our eye into the macroscopic world, which is quite already you have learned a bit from Ogisa Sensei or Professor Ogisa's talk, but I repeat. Okay, so here I listed some physical property of lovely materials. First one, large deformation is possible. Yeah, as you can feel like in our daily life, only the rubber can be stretched like very long. No plastics, no metals, no ceramics, only rubber or gels. So it's a kind of the extreme the property necessary for some components in your robot. Maybe that's the reason why you use rubber. With this the property, I guess. And also, when you stretch, you don't need so much force. In other words, the modulus is quite low. And the value is like in the megapascal level, or 10 to 5th to 10 to 6 pascals. And elastic modulus is temperature dependent, and which is proportional to the absolute temperature. So if you increase temperature, then the rubber elasticity get a bit higher, be proportional to the temperature. You can check it if you wish. But now you also understand from microscopic viewpoints, because temperature get higher, then polymer chain movement also become very, very active. Then they further try to shrink. That's the reason why this modulus value increases. Okay, and we did a small experiment together, the Gaff-Joule effect. This only happened in rubber samples. And finally, we don't see so much volume change upon stretch when you stretch a rubber band. No need, maybe, but I just show you. Please have a look at this one. So now, please have a look at the size, diameter, or this rubber band. When you stretch, of course, it will become thinner, right? Then if you measure the how much shrinkage and how much elongation, then you can calculate the volume. Then we know volume doesn't change. Oh, just a moment. Where is it? Just a moment. Oh. I once again share my slide. Okay. Okay. When you stretch, of course it's become longer in the elongated direction, but it gets thinner to the opposite directions. And as a result, the volume doesn't change. If we use technical term, then Poisson's ratio is nearly equal to 0.5. I now explain it later. So now you can looking at the tables with comparing the modulus values and Poisson's ratio for the different materials. For example, the steel, of course, it's very hard. It's not in a megapascal level, but 1,000 times larger and multiplied by 200. So it's quite the hard, 200 gigapascal. Aluminum or the silica, these are really hard materials. And polystyrene is one of the plastic material, polyethylene, also the plastic. PVDF is also another plastic material, which is in the range of gigapascal level. But only rubber show the very low modulus value. It's about 10,000 times smaller than a plastic moduluses. And also, more interestingly, Poisson's ratio is totally different. All of the other the materials has the value of Poisson's ratio about 0.3 to 0.4. But only rubber give this Poisson's ratio near to 0.5. What does it mean? So first, we need to define what is the Poisson's ratio. So here, this slide shows this definition. So now, think about we have a kind of cube structure with the size 1. Any unit is fine. 1 millimeter, 1 meter, 1 centimeter, 1 nanometer. Nanometer is not good, but 1 micrometer. Then, if you stretch, then of course it's elongated to this direction. This cartoon figure is too much, but anyway, we may be able to write it's the 1 plus epsilon, and then epsilon is called strain. Then, of course, into the elongated direction, the epsilon value become positive. But at the same time, usually materials dimension decreases in opposite directions. And then we may be able to write it in this form, 1 minus epsilon dash. Then the Poisson's ratio can be defined in this equation, the ratio between epsilon and epsilon dash. Now the time to calculate the volume change with this equation. Original volume V equal, of course, 1 by 1, okay? And then how much is the delta V? So after elongation, the volume of this one is 1 plus epsilon and 1 minus epsilon squared. And because we want to look at the difference between the before and after, so we subtract 1 in this formula. Then this formula can be calculated in this form. Then if nu equal to near to 0.5, which means that the delta V become nearly equals to 0, which means rubber doesn't change the volume, and if we use a technical term, it's incompressive. Then compared to that, some other materials like the Poisson's ratio over 0.3, 0.4, by substituting such values in it, then delta V also basically becoming a positive value. Why volume increases? Can you imagine what is happening inside this material? Yeah, of course. What to say? Mass doesn't change. So which means that the density decreases. Why density decreases? Huh? Uniformly? Maybe not. There would be a hole in it, void in it. Stretch sample may contain many voids inside. That's the reason. The Poisson's ratio sorry, volume change become positive. Okay. There is another material. I don't say this is material or not, but material, let's say material, which shows incompressibility. What is it? Yes, of course, it's water. As I mentioned, rubber has some relevance with the liquid materials. So why rubber has a similar property? Now I think you can understand. Because they are really, really mobile. So if they find voids, then they comes into such places, like in water. If you cannot put the water, but water can change the shape depending on vessel, cups, whatever. They can change the shape as you like by just having the different shapes. There is no void in it because water molecules can cover such holes, voids, at any time very quickly. Like in this water case, rubber can also do the similar. So by having this result, you can also say yes to my comment that rubber is liquid. Okay. Now you may know this one, but I continue. So there are many different type of the stretching the style. The one is this one. Oh, sorry, I don't know how to say it in English. Unidirectional stretch, yes, and the shear stretch, shear, and also this. So I forget how to say in English, but you can judge from Chinese characters. Okay. Then there are in any case, if you give a force, then they have a restoring force when it gets back. Then if you apply force in this direction and area is this, then force divided by area is a stress. And the stress and strain has a linear relationship. If the strain level is small enough, then this proportional constant is called Young's modulus, as you may know. And also, if you give a kind of this shear deformation, then a similar equation can be made related to the shear stress and the shear modulus, shear strain, and the proportional constant is called shear modulus. And this E, Young's modulus, and G, shear modulus, has a very simple relationship in this way. And here, Poisson's ratio also plays a very important role. G and E has this relationship. So if you know E, then you can also calculate G. Well, anyway, in case of lava sample, plastic sample, new value is like 0.5, 0.34. Then the G value and E value doesn't different so much. Just a case of a lava case, by substituting 0.5 here, then the G equals to E over 3. So just a 3 times difference. Okay. Then now we think about this the deformation. Then this is because you know that you give a kind of the static pressure from outside to change the shape of material. So we can call this deformation as this Chinese character, sorry. And then I just forget about how to say it in English. But anyway, and then the proportional constant can be called as a bulk modulus. Okay. But here, there is a very interesting correlation between this bulk modulus and Young's modulus. Because the bulk modulus and Young's modulus has this relationship, then try to input the 0.5 into the Poisson's ratio, what's going to happen? B value goes to infinity. Of course, it's not happen because as I wrote, the lava it's not perfectly 0.5, but depending on the material, but it can go to 0.4999 or something like that. That is maximum value. So then finally, what we can say is at least the bulk modulus is much, much higher than Young's modulus. And Young's modulus is always megapascal level. Then the B value can go beyond the gigapascal range. So, which means if you want to compress the lava from all of the directions, it's really hard. You cannot push the water. Just to imagine that the inside the syringe, the full of water, and then you try to push piston to try to change the shape, but you cannot push if there is a water in it. If it is just a gas, then you can very simply push it. But case of water, liquid, then you cannot. So it's quite similar relationship. And there is a very, very nice industrial application of this relationship. What is it? This is seismic isolator. In Japan, as you know, there are so many earthquakes, so many of the buildings or bridges, we have to set this seismic isolator beneath the buildings or bridges. Then upon the earthquake, then this portion moves. And of course, energy must be dissipated. But the point is you are now, there is a huge object on the top of this rubber base material. Of course, this is not just simply rubber, but it's a kind of lava steel sandwich-like structures. But it can bear the very heavy object without deforming, without pushed. This is simply because this, in that case, in this vertical direction, B plays very important role. But upon the earthquake, it can move left and right, because in this case, E plays a role. So this difference can be nicely applied to these seismic isolator systems. Who thought about it? Very nice design. I don't know who thought about it, but he should be very clever guy. Okay. Now, we want to also start to discuss something different. The technical term is viscoelasticity, which was already mentioned by Professor Kuboyama in the morning. And also tomorrow or day after tomorrow, I don't remember, but another professor in your university also talking about something about the viscoelasticity. But I just briefly talk about the viscoelasticity from using one interesting example. So which is the comparison between the bouncing lava and non-bouncing lava. Actually, I have this one here, but I also prepared a video, so please have a look. So first, I show you the response of a bouncing lava. Yeah, it's common, okay? We call this in Japan super ball. How do you call it in Taiwan? But anyway, this is non-bouncing ball. Okay. Question is, where has all the energy gone? You brought up gave a potential energy, but that where the energy gone? one question. And also, now I'm heating this non-bouncing ball. Oh, it was not sufficient. So once again, I heat this non-bouncing ball, putting it in a boiled water, then start to bounce, like in the case of a bouncing rubber. So the property of this bounce or non-bounce is temperature dependent. Then after that, I place it into, yes, liquid nitrogen to cool it down, to lower the, how much? Like minus 100, minus 200 degrees C. Then please listen. Yeah. The change of impact sound become different in the case of a rubbery situation. And now this sound is like the glass ball or the steel ball, quite similar. Actually, if you cool the rubber, as I mentioned, phenomena is temperature dependent. And if you cool down the rubber ball, it turns into the glassy state. Okay, so you are using rubber as a component, but be sure that you are using this rubber in a room temperature. Otherwise, the property become different depending on what kind of rubber molecules is used. Actually, these two rubber is made from different polymer chains. The bouncing ball is coming from the butadiene rubber, and the non-bouncing ball is coming from the isobutadiene isoprene rubber. You don't have to remember the name, but they are different. And also it is the chemical structure is written here. But can you imagine why left-hand side one finally shows bouncing nature and the right-hand side one doesn't? You may not know. Yes, of course, because I also don't know why. Yeah, this is very important discussion that chemists usually produce new material based on the new chemical synthetic route, and they show us some interesting the new materials, and then sometimes the material property totally becoming different from the ordinary one. But usually, it's really, really difficult why it happens. Not so easy. We can, by analyzing the chemical structure, we can write this type of chemical structure, but it's very hard to correlate this chemical structure and mechanical property. It's ongoing, kind of ongoing project for the human beings. Okay, anyway. Yeah, yes. So this is a summary of the temperature dependent change of the this type of polymeric materials. So when we call rubber, this means that at the room temperature, it's rubbery. But even if the case of the rubbery material cool down to enough low temperatures, then it turns into the glassy state. And the modulus value is the megapascal level in case of a rubbery, but goes to very quite higher, 1,000 times higher, and the glassy state with the gigapascal modulus values. And of course, the Poisson's ratio also changes from 0.5 to 0.4, 4.3, depending on the material. And also at some temperature range, of course, there is a kind of transition range, which we call the glass rubber transition. And here, if the material is in this state, energy is really, really dissipated. So in case of rubbery situation, like in the bouncing ball, energy is stored, and then stored energy is released, and then which turns into the get back the lava ball into the potential energy. But also in the glassy state, the ball was bouncing because in this case, of course, the mechanisms are different because you can hear the different sound in case of the lava state. But even though the glassy ball can also bounce. But if you are in the material is in this glass lava transition state, then it turns into the non-bouncing ball. But question is why here the energy is so much dissipated. This is what Kuboyama sensei tried to explain with using a toy model, so-called the Maxwell model. And once again, I repeat this discussion. Although I will not go into the detail because I hope the another professor tomorrow will more detail discuss about this portion. So, but anyway, this is one of the toy model expressing of the polymer samples viscoelasticity. So, as you remember, Kuboyama sensei used two different components, spring and dashpot. And here, Zena model contains two spring and one dashpot. So a bit complicated model than the model which he showed. But anyway, by having this model, we can reproduce this relationship. Here, please have a look at this. The lateral axis is temperature and vertical axis is a modulus value. And if temperature increases, then the glassy material turns into rubbery and further melt condition, you can quite easily imagine it. But if you draw the graph in terms of the frequency, then the shape become opposite. So I just for your reference draw the tendency. So as we saw already, at the low temperature the modulus is high, and high temperature the modulus become lower, and here is a grand transition range, and which correlate. Kuboyama sensei tried to explain it, but if you take a long time observation, then the sample looks like the soft, and but if it is short time, it behave like a hard material. And in other words, the low speed, high speed give a different the responses. That is a very interesting point of this toy model, and which hopefully explaining the phenomena occurring inside the material. But please don't believe that there is a spring inside the material, dashpot inside the material. This is just a toy model, okay? But of course, as we already have looked at from the first half of my presentation, the spring is of course related to a chain, polymer chain elasticity. As we saw, sorry, I'll get back here. So as we saw, even experimentally, we could look at the relation, the linear relationship between elongation and the force from the single polymer chain. Then, of course, these components is so much amount of these components is existing in the rubbery material. So rubber material can also show the spring-like nature. But what is this the dashpot? The dashpot originally just represent the Newton's viscosity. So as in your daily life, as also he explained about the case in your daily life, when, for example, in a bathroom, if you go to bathroom and you move the hand in a water, then if hand doesn't move, then hand doesn't feel any force. But once you start to move your hand, then your hand feel the force. So the force and the speed has the proportionality to each other. So this dashpot is quite similar, the one. So here is the oil in it, and then this cylinder moves, then this feels such kind of resistant force. That's the meaning of the dashpot. But what is that in reality inside the real material that can be correlated with this cartoon figure? So because as we already saw, the inside this material, polymer chain is moving, and there are so many polymer chains, then they have a kind of friction to each other. Then, of course, this is also go to energy dissipation, the heat generation. That's the original molecular level, the interpretation of the viscosity. Okay. Then coming back here. So this Zener model can express the toy model. So I repeat, there is no spring, no dashpot inside. But yeah, we can use this model to just simply explain the phenomenon, macroscopic phenomena occurring, observed for the macroscopic observations. Okay, then because this Zener model is a bit difficult to understand, so the Kuboyama sensei used the Maxwell model in the morning session, and then the Maxwell model also show a similar tendency in frequency or temperature. But anyway, difference is at the high speed or low temperature, the modulus exists, but at the high temperature, low speed, modulus, the value get closer to 0. That's the difference. But by just looking at this is not good enough. So I also prepared the kind of the simulation results. So now this is a high frequency region. So now you get this portion and move this portion right and left repeatedly. Then please imagine what happens if you do this very quickly. Here inside, there are very viscous oil in it. Then I now start this moving. Yes? Now you're looking at the spring is moving very quickly, but the dashpot portion doesn't move so much because this highly viscous liquid prevent the move this portion quickly. So only spring is the chain have a deformation. So in high frequency range, this Maxwell model show elasticity. So elasticity dominates the phenomena. Then what happened in a low frequency region? Sorry. I didn't mention that. I just added this several slides during lunchtime, so you don't have this portion in your handout. Sorry. And anyway, the case of low frequency, then you can move this portion very, very slowly so that the spring doesn't elongate so much, but just move this portion. You can do like this. Then, because it's so slow, then force exerted on this dashpot becomes slow. Because now you are moving your hand in the liquid very slowly, then you almost no feel the force. So this is a situation corresponding to this region. Then what's going to happen in the middle frequency region, which is also correlated to glass transition states? Look, both spring dashpot move with some level of speed. Then the spring is okay because its energy just stored. But the case of this dashpot guys, they only energy is dissipated. So only at this middle frequency range, the energy is dissipated. Inside the material, the friction between the polymer chain enhanced, and it generates heat. That's the reason why non-bouncing ball doesn't bounce. Okay. Now, let's get back to our slide. Now, I hope you think about these two the bouncing ball, non-bouncing ball, how we can apply these two materials. How can I apply these materials to which field? Now, I show you the movie. Two different, these are bouncing, non-bouncing ball. If you start to load these two, then the distance become totally different to each other. Think about it. It's already used in the industry. Yes, the bouncing ball is used the summer tire, and the non-bouncing ball is used for the winter tire. Oh, I don't know, in Taiwan, you have much snow or not, but in Japan, we have snow. Then on a snow road or icy road, then energy must be dissipated to quickly stop the automobiles. So energy dissipation should be very high level. That's the reason why such kind of highly energy dissipating the material is used for the winter tire. But in summer, of course, the energy consumption must be minimized. So the bouncing ball with small energy dissipation must be used. So viscoelasticity also plays a very important role in thinking of the industrial product design. Okay. And here, from now on, I show you one striking the movie. So if you don't like it, then you can close your eye. So it happened in 1986 in United States. And some old professor may know this accident. The Challenger is a space shuttle. It happened when I was young.
And liftoff of the 25th Space Shuttle mission, and it is cleared to...
If you don't like it, close your eye. Oh, sorry. Yeah. It's suddenly explosion of that. When I was a kid, I was watching the TV news announcing this accident. Why this accident happened? Of course, the investigation committee was formed. Oops, something happened. Oh yeah. And that the fireman, I showed his photo at the beginning of my presentation today. And once again, he played a very important role as the head of this investigation committee. And he did the quite similar experiment with what I did. The putting the lava into the liquid nitrogen to cool down it. Then what happened? Lava is no more lava, but turns into glass. Then because space shuttle also contains a lot of lava material in it. But if you, of course, the space shuttle go up to the space, then the temperature get down, then the lava turns into glass. So it lost the physical nature as a lava material. That's the main cause of this accident. And he said, because nature cannot be fooled. Yes, that's right. So if you are using the actual materials, then you need to really understand the perfectly the material's nature. For example, this product is used where, what kind of environment to get temperature become higher or lower. Everything must be taken into account when you design any kind of products. So this is what I want to mention to you. The actual message to you this time is please remember the responsibility once again as a scientist or engineers to the society. So this is for me a quite important message for during today's the lecture. Okay. So now let's move on to the next the topic. And also this was also already made by mentioned by the Kuboyama sensei in this morning. And he said he also saying that I will put the same question, and I once again put the same question here. So why tires are black? And as he mentioned, in 1904 there was a big invention. Before that, the color of the tire was white, and it turns into black by some invention. And before, first of all, as you can see, the color of a rubber band, original color of the rubber is not black or white. You add something in it. In case of a white tire, calcium carbonate particles added. Calcium carbonate. But in 1994, someone found the carbon black addition to the rubber gave quite high enhancement of the mechanical property. That's after that, all of the tire, the color became black due to this carbon black. But why people add the carbon black to rubber samples? That's quite simple reason. Just imagine if you make a tire product just by the natural rubber or synthetic rubbers, you know that the rubber can be also used erasers in the past. So if you give a kind, you know that on the road, it's easy worn out, disappear, even maybe after 1 kilometer drive, maybe. So people are not safe with that. But by adding particle into the rubber materials, even in case of this white tire, it was okay. But nowadays, our daily life product tire, not so much quickly worn out, even after driving several hundred kilometers, but maybe worn out level is just less than millimeter, I guess. Such a very big progress, improvement was made by this invention. Just a moment. Sorry. My room's air conditioner gets stopped automatically, and the room temperature gets become high so much, and so now I restart the air conditioner. Sorry. So, so coming back here. So then I now try to explain why this happened. Yeah, even now, people, rubber scientists do not perfectly understand why addition of such small particle into rubber particle can enhance the mechanical property of this rubber product. No one knows. Very interesting. Could you imagine the invention of the effect was more than 100 years ago, but we still do not understand the real reason. But anyway, now, as I introduced at the beginning, I now start to discuss about this Einstein's achievement. Einstein, you know him very well. The relativity law, also the photoelectric effect or Brownian motion. He produced 3 very important papers in 1905. And he became quite famous in the scientific field. But at that moment, he didn't have the doctor degree. Then the Zurich University wanted to give him the doctor degree. So the university asked him to write some new paper, different paper. Then the Einstein selected this subject. The title of his doctor thesis was A New Determination of Molecular Dimensions. Wow, so nice title. How to determine the size of molecule. And finally, he get this equation. Now I let you know. His subject was this. Why? Water is viscous. Of course, a bit viscous. But if you add sugar into water, then the sugar water become more viscous. And he investigated why this happened. Yes. And finally, he wrote, could derive this equation. The eta is the water viscosity, and eta star is the sugar water viscosity. So how much enhancement that can be written in this way, and phi is a volume fraction of added sugar. And this equation is very simple, but the derivation process is very difficult. So to be honest, I also do not perfectly understand his paper. But anyway, later on, some other researchers learned about his equation, then just imitated his the derivation process and applied it to a different field. So if the small particle is added into the liquid medium, then its viscosity increases. Then similar may happen when you add the hard particle into the soft medium, elastic medium, then the modulus value of the such a composite material increases. Quite simple analogy between. Then the goose and gold finally get this equation. So this is one of the possible solution of the how to explain this reinforcement effect. But reality was not so easy. This is experimental result. So by adding, by changing added Filler level, then how much the modulus value increase was observed. And this is experimental result, but Einstein's equation, Goose-Gold equation cannot explain perfectly. So we need to modify their equation, but no one still succeeded in it. And once again, coming back to my research, as I mentioned, I use atomic force microscope and not just looking at the structure, but in this case, I push that the very sharp AFM probe to this material one by one, next by next. And then because you know that you are now pushing with a very sharp needle, then you can have a nanometer scale resolution, modulus mapping like this cartoon movie, and finally get this type of experimental result. Then this is the carbon black field, not lava sample, with before and after stretching event. And I will not go into the detail, but we can visualize this type of situations. And then the blue region corresponded to a soft lava, and brown region corresponded to added hard fillers. But also we can find some kind of interfacial region in between, and which is not discussed in the previous theoretical treatment. So because there are so many green regions, then we need to put this interfacial region into account. And also, if you stretch this sample, then we also find a very interesting result. By looking at this stretch situation, this is stretched in this direction, this direction, then some portion get as is shown in this color. The blue means soft and green means hard. Then originally all of these portions were originally blue, soft. But upon the stretch, then some portions start to bear the macroscopic stress. So this is very interesting nanoscopic world observation. Not all of the area respond to the macroscopic stretch, but some portion just remaining untouched. And these portion only try to get the hard work. Like in a human being, you know, that if you have 100 people, then not 100 people work together, but someone work very hard, and someone else is just get sleep or something like that. Similar things also happening inside the actual material. That's very interesting. And due to time limitation, I cannot go into the detail of this discussion, but similar the interesting discussion can be also happen in the biological related field. So I think this the story can be also found in English literature, so you can find it. But this professor in Hokkaido University has a survey on society of ant. And then when he looked at the some kind of colony, then always he find the 20% of the ant doesn't work. And the rest of 80% is working. But if you to pick up the lazy workers from different colonies and get them into the one colony, then what's going to happen? This colony will die, but no. Then 80% of the lazy ant start to work. Very interesting. So this means that 80% to 20% relationship may have some biological meaning. That was his research point. Yeah, and I will not go into the detail of answer of his the idea, but if you are interested in, please have a look at this paper. But what I have get from his discussion was that when you make a material, then the material scientists try to achieve a kind of 100% performance from this material. But by listening about his talk, I start to change my mind. For example, coming back to this one, so people try to make this lazy rubber matrix must be work together with others. But I think this portion may also have some meaning. So that is something that I'm working on. So yeah, forget about that. Okay, just a moment, because I have to close my talk. So finally, yeah, I just want to show you several the movies. This is also get from the company side, YouTube movie. You can also check. So this is the design of future tire. Look at. In some future, shape of tire will become spherical. They think this quite hard. And if they can make this type of spherical tire, then everything gonna change. So for example, yeah, maybe this type of movement can also become possible. Look. Yeah. And also maybe interestingly, yeah, have a look. Look. Here. Yeah, this type of the driving also become possible. Although maybe human being cannot follow, but maybe AI technology can, with the help of AI technology, then maybe this kind of future can be possible. And also this movie also shows the kind of automatic detection system of the broken area. Look, so now due to that the glass piece, then the lava portion was damaged, but lava by himself reproduced that region, repair that region. That is a future. And also, as a material scientist or also engineers, we need to, think about the future and also put the future in your mind, and then you can find the appropriate direction. That is maybe the appropriate way for all of us for a bright future. And if you have any time, then please check this Professor Ishida's mention. He always mentioning such kind of issues. And also finally, I show you that the company's challenge, which is also very nice, that the cartoon movie was not just imagination, but this company already have this. Even after cut, after waiting 1 minute, then, yeah, this way. So if you have a bright future, then you can find a better design or better material, and also try to give your effort to such directions. Okay, so this is what I wanted to say. So this is a very last slide. So today I was talking about the polymer science, especially on the lava science, but sometimes you need a physics, chemistry, and I didn't mention anything about the mathematics today, but also some kind of analogy with the social science, the society of art. We can learn many from different fields. That is also what I wanted to mention. So you are kind of robot engineers, but please also study a different field so that enrich your knowledge, and you may get some new interesting ideas from a totally different field. This is what I wanted to say. Okay, that's it. So this is the final the slide with a description of the homework. So I just want to listen what you felt during my lecture and submit a short comment with less than 100 words. That's it. Thank you very much for listening.
Okay, thank you so much, Professor. Okay, I think this really interesting and also is impressive for us, especially you provide many interesting examples, and also I totally agree that we can learn a lot from the other maybe research field or other area.
Thank you.
Is there any question? the student over here and student online. Any questions? Uh, 助教可以帮我看一下线上的学生有没有问题？ Okay, okay. If there is no question, thank you so much, Professor Nakajiwa. And over here, I think we could take a break for 10 minutes. And the next lecture will start at 5 minutes later. Okay. Okay. Thank you again, Professor. Looking forward to seeing you if you could come to Taiwan maybe next year.
Yeah, 谢谢。再见。
Okay. See you.